Okay, thank you so much. Thank you, John. Thank you all for coming. Thanks for those here in the room and those online. We are very happy to have our speaker today, Dr. Chris Ruff from University of Michigan. And Dwayne is going to introduce him in just a moment here. I just want to say that we appreciate you participating in these distinguished climate lectures. We have these scheduled generally monthly. We have currently a schedule through June, and once the talk is done, in another few days to a week, they end up online, and we have them if you want to view them. They're viewable online, and so that's going to happen for this one as well. And again, thanks for coming. Thank you, Dr. Ruff, and thank you, Dwayne. We'll introduce him. Great.
Hi, thanks, Margaret. For those of you who don't know me, I'm Dwayne Walliser. I work in the Earth Science and Technology Program Office, and it's a pleasure to be invited here to introduce Chris Ruff. Chris is the Frederick Bartman Collegiate Professor of Climate and Space Sciences at the University of Michigan. Turns out he did work at JPL at one time, as well as Penn State, and I tried to find where I could what you did at JPL, and I couldn't readily do that, but maybe when you're up here, you could just sort of highlight that and give some touchstones for people of what you did when you were here. His research interests involve remote sensing of the Earth from space with a focus on ocean and atmosphere applications and the sensor technology development. That'll be very evident from his talk and the fact that he's PI of the Cygnus mission. That was an Earth Ventures mission. That's been up for several years now. I think are you going through senior review now?
Yes, right now.
So he's putting in a senior review proposal. He's a fan favorite kind of amongst NASA, exemplified by 8 NASA Group Achievement Awards. He's actually even the IEEE Geoscience and Remote Sensing Society's Best Journal article and Best Conference paper in 1997 and 2007, which he gets his hands dirty, you know, in a way that excels, also excelling. This is a good one. He was an AIAA Best SmallSat Mission of the Year award in 2016, obviously for Cygnus, right? Unless you had something else that I didn't know about. He served on the CSAS, so that's actually one place I've met Chris, is serving on the Committee on Earth Science and Applications from Space, the Academy panel that we worked on together, and that's, I learned a lot about Chris and admire what he brings to a panel like that. He was also on the Earth Science Decadal Survey, both the last one and the one previous to that. I know in the last one, the 2017 one, I think you were on the climate panel, is that right?
Yeah.
And so in those interactions, actually, we asked Chris to participate in our KISS study on continuity that occurred over the last year. He was a great contributing member for that activity, which will be done soon and reported out. And so we're fortunate to have Chris in sort of an extended visit at JPL for about 4 months, and appreciate the work by Shannon Brown, his colleague, to help bring him here and help support his visit. And part of having him give this presentation within the Climate Center at the forward half of his visit is to help establish what he does and any kind of interactions that may develop from this. So we encourage you to listen to this seminar. Know that Chris is around JPL for the coming couple months, maybe about one more month, and don't hesitate to reach out and engage further with Chris. Anyway, it's a pleasure to have you here, and thanks to the Climate Center for hosting this seminar.
Thanks. Thanks, Dwayne. Thanks, Margaret, for inviting me. And yeah, thank you all for coming. I'll just say a few words about my time here at JPL back in the early 90s. I came here right after grad school, and I worked, I did kind of 50% of my time on small technology development things in passive microwave radiometry. And about half of it was spent working on one mission, TOPEX. I was the instrument scientist for the TOPEX radiometer. And that's when I really first started getting involved in flight work. And then I continued on with that role for the JASON-1 mission as the radiometer lead. And that was after I had left here. And then with JASON-2, that's when I started working with Shannon Brown, who's my sponsor here, and he was a grad student in my group at Michigan. And he sort of took over a lot of the work on JASON from me, and then after he came here right after grad school, and I kind of backed off and let him run with it. So yeah, that was my time here. Yeah, so today I wanted to talk about Cygnus, but I wanted to put it in a little bit of context as kind of a case study of something more broad and general and trending with satellite technology and where things are going, or I think things are going with satellite technology in general, but earth science technology in particular, and that's small satellites and constellations of small satellites. Let's see here. What did I do with my pointer? I don't know. Maybe I can. Oh, sorry, I got it. Okay, so so a little context, just going back in time a little bit. Prior to about 2000, which is sort of the birth of the beginning of the CubeSat revolution, as I would call it, almost all scientific satellites that were flown, certainly to other planets, but also around Earth, were custom designed, individually designed buses, and often the instruments were also individually designed for the mission. Sometimes there was more than one, but more often not. And what happens when you have these customized one-off designs for an entire mission is everything takes longer and costs more money, because you have to do all of the details of the design and the building and the testing customized for that one time and figure out how to do it the first time. And basically everything involved in the mission execution has NRE attached to it, everything, because you haven't done it before. And that tends to make things take longer and cost more money. And the typical time from start of mission to launch, this is actually pretty generous, 5 to 10 years. There are very few that are only 5. I mean, 10 to 15 would be a pretty reasonable range for a lot of these big ones. And this is an example of one of the sort of whopping ones that went up a while ago. It's still up now, Aqua. And you can, probably most of you are familiar with this satellite, but there's a whole bunch of instruments all loaded up on the Earth-pointing side of this thing here, and it's huge. It's heavy, 3,000 kilograms, lots of power, lots of cost, and there's a lot of really great things you can do with a satellite like this in particular, because there's many, many sensors all looking at the same thing at the same time. So you have a lot of constraints on physical processes by looking at it at a lot of different angles, where by angle I mean frequencies and polarizations and measurement types and all those sort of things. So it constrains the heck out of the process. So it's a really good thing for type of measurement for process studies and understanding. But at $1.6 billion a pop, you could not fly a large constellation of these. And if you can't do that, you can't do things like get revisit time down to an hour instead of 3 days. And just things like that are just never going to happen. Okay, so the birth of the CubeSat happened right around the same time as that. The first CubeSats were developed at 2 universities here in California, Cal Poly and San Luis Obispo and Stanford. And a lot of the motivation from it, talking to people that I've talked to who were there in the early days when they were first figuring the whole thing out and sort of inventing the U, 10 by 10 by 10 centimeters and so on. A lot of the motivation behind this was because of that 15-year time it takes to get to launch, and then you just start getting data. It's absolutely impossible to have a student be involved in the conceptual design, the building, the testing, the flying, and actually looking at the flight data. You'd need to have some lifer grad student that's in grad school for 15 years to be able to do that, which sometimes happens, but it's pretty rare. And even more so with undergrads who maybe they can get involved in a project when they're a sophomore, but they're gone in 2 or 3 years, right? You'd never have them get involved in something all the way through the whole life cycle. So that was a lot of the motivation. My understanding is of the whole idea of these CubeSats was you can come up with an idea and start getting flight data before a senior graduates if they start working on it as a sophomore. And there was a few things that really allowed you to condense down the timeline of the development. And one of them, I think, one of the main ones was the standardization of a handful of key things. One of them is just the size of the thing, this idea of a 1U, a unit of volume, and having it be fixed so that there was no design issues about how big the thing was going to be. You knew it was going to be a 1, a 3, or a 6U, and so you didn't spend time figuring out how big it should be. The way you got it into space was standardized. There were these Peapod deployer things that had standardized interfaces. Just a whole bunch of stuff was standardized, so you could just get on with building it and not have to do this high-level conceptual design study first. So the first CubeSat was launched in 1998, and then a whole bunch of them went up after that. This is a few years old now, but the early stuff before 2018 is all actuals. And these are the first two that launched right here. And then if you look at these colors, yellow is a university launch, and they're mostly university launches early on. And then blue is private industry, and you can see the blues start to grow and grow and grow in the mid-teens. And then NASA and ESA primarily are the whatever that is, dark purple, and those are the ones down at the bottom here. So places like ESA or NASA or JPL have started flying CubeSats, and there's more of them now. But you can see that it's still primarily dominated by universities and private industry. But I think the real takeaway is there's just a whole bunch more of them now. Yeah.
Just a question. In the university cases, where do the launch services typically come from?
A lot of them are the Air Force, actually. But I mean, they're these standard, these deployment mechanisms that you get loaded into, and then you just wait. And they go up there, and they get deployed often from the space station, and they take, you integrate it into the deployment module, the deployment device, and then wait around, and a few months later, your data starts to flow. And everything that happens after you plug it into that little Peapod thing is someone else's problem and someone else's budget too. So that really simplifies things for a university lab to do these sorts of things. Yeah, it really opens the door to a lot more participation, so it's a great educational value for students. I mean, we build CubeSats at Michigan, and it's a really wonderful way to train students, and it's really sort of secondary for educational purposes. It's secondary whether the thing works, because you learn so much getting it built, and if it does work, all the better. And if it works a little and there's problems, you actually learn even more because you look at what the problems were and so on. But flying things that have high quality, scientifically useful data is really, especially in the early days, was kind of an afterthought. And that's really changed a lot in the last 10 years. Okay, so here's just some pictures of CubeSats just to give you the idea of the scope of things. This is 10 by 10 by 10 centimeters, 1U. Here's a 3U. This 6U was built here. This is the RAIN Cube satellite, which was really successful. It's got this deployable K-band radar dish, and it's actually now sort of launched into a new life in private industry. There's a lot of tech transfer that happened, I think, from JPL out to industry, and a bunch of these are, there's a plan to fly a bunch of these, I think, at Tomorrow I/O. I think they've picked it up. Anyway, there's what they look like. Okay, so now I'm going to switch to describing the Cygnus mission, and then I'll come back at the end to sort of how it fits into the growth of things in general with smallsats. Okay, so the original concept for Cygnus, which was in the original mission proposal, was to measure winds over the ocean in heavy precipitation and to measure them often. And the reason was to measure winds in the middle of tropical cyclones. So in the inner core of a tropical cyclone, it rains all the time. So you need to be able to see through rain, which means you need to operate at a low frequency, long microwave wavelength. And then you wanted to measure them often enough to be able to capture short timescale processes, in particular the rapid intensification phase that might happen over the course of, I don't know, maybe 18 to 36 hours, somewhere in that range. And if you have, a single satellite in polar Leo and you come around every 3 days, you could easily miss it or certainly alias it. So the way to deal with that is with a constellation of satellites. Okay, so we need a constellation, and we needed to operate at a low frequency to get through the rain. And the design concept we chose was first 8 satellites to get the revisit time, a shallow orbit inclination, so we spend all our time over the tropics or near tropics where the hurricanes are to improve our revisit time again. And then we use this relatively new kind of remote sensing technique, this bistatic radar, where the transmitter is the GPS constellation. So all we're flying are modified commercial GPS receivers that have been modified to look at the scattered signal off the ground. And so this is an example of the kind of thing, this sort of, oddball, non-standard remote sensing technique. It's not something that would, I think, ordinarily or maybe ever get approved for a mission that costs $500 million or $1 billion because it's not a proven technique. It's a risky technology because it's a new technology. And that's one of the kinds of things I think that gets enabled by cheap missions, that you can try things that are unusual. Anyway, so that was the remote sensing approach. And then since we've been up there, we were designed, the mission objectives were all focused on hurricanes, but it was much simpler in the way we designed the operations of the mission. It was much simpler to just leave the thing on all the time and bring the data down. So we have 24/7, 100% duty cycle data. So some thousandth of a percent of our data or something is actually over hurricanes. And we have all this other data over the ocean and all this other data over land. So over time, we've kind of expanded the scope of the science by looking at the data in other places. And so I'm going to give a bunch of examples of that, as well as some examples of the hurricane work that we've been doing. So yeah, the mission timeline. We had our project start in December 2012 and launched 4 years later, so a little bit shorter than that 5 to 10 year range. We transitioned. We had our early on-orbit commissioning for a few months, and then in March 2017, we started our science phase, and we've been in Phase E, extended Phase E ever since, and right now, we're writing our senior review proposal to get another 4 years of funding going on into the future. Okay, so this is just kind of a cartoon about the idea of GPS-based bistatic radar. So the GPS satellites are running all the time. Our Cygnus satellites are someplace else over here. And at any instant in time, for any pair of satellites, a transmitter, there's about 31 or 32 GPS satellites, and then there's 8 Cygnus satellites, where there were 8 until last November. Now there's 7. And for any pair at any instant in time, there's going to be one spot on the ground that's the specular reflection point, right, where the angle of incidence equals angle of reflection. And if you work out the phase function of the bistatic scattering cross-section at this point, about 99.5 to 99.95% of the power scatters in the forward specular direction until the wind gets really high. So almost all of it. The amount of power that scatters in the specular direction forward, it's typically 25 to 35 dB higher than the amount that scatters back towards the transmitter, which is a standard monostatic radar, like an ocean scatterometer. So we have a 30 dB advantage right off the bat because the signal going forward is so much stronger. And that means 2 things. 1, you can get away with a much lower power transmitter. And 2, you can get away with a much lower gain antenna on your receiver, so you can have a small antenna. So there's a bunch of enabling things right there by using the specular geometry. Okay, so this is just a picture at optical wavelengths of forward bistatic specular scattering, right? Here's the moon here that you see directly, or the camera sees it with direct line of sight of the light scattered, from the sun to the moon to the camera. And this moon down here is bistatic specular reflection, where the light goes down, hits the lake, and then comes up. And that moon right there is pretty smooth. It's a little bit rough around the edges, but it almost looks as sharp as that moon. And that's because the water is really smooth. It's glassy. And actually, if you zoomed in really carefully on this picture and looked at the exact shape of the roughness around the edges, you could calculate the roughness statistics of the water, and you can calculate how windy it is over that lake just from this picture, okay, at optical wavelengths. And then when the wind blows, you get diffuse scattering instead of specular scattering, and the scattering spreads out all over the place because of all these tilts in the water surface. So, the specular point might be right about here, but because the water is tilted all over the place, you get all this other scattering around it. And if you can image that scattering cross-section as a function of position away from the specular point, you can calculate the roughness statistics, and you can calculate the wind. And that's how Cygnus works. And this is an example of, let's see. Happened here. Sort of stalled out. Oh, here we go. I don't know what that was. This is an example of just one data sample from Cygnus of the scattering from the ocean caused by GPS signals hitting the ocean, scattering up and being measured. And we make one of these measurements every half second from each GPS transmitter to each Cygnus receiver, or most of them that we can see. And from this data, you can figure out how windy it is, basically. There's a specular point right here, and all this stuff away from it is diffuse scattering away from the specular point. These two coordinate systems, this course acquisition code chip, that's just GPS jargon. That's basically the range gate of a radar. This is range. So this is the specular point here, and then at higher ranges, longer ranges, this is scattering away from the specular point at other places in the ocean. If you go above the specular point to shorter ranges, that's the atmosphere above the ocean, and there is no scattering, not at these frequencies. And then this is the Doppler shift of the signal on the surface. So we have a bank of Doppler filters and then range gates, so you can generate these two-dimensional images of the scattering cross-section, and that's what we get the wind from. Okay. All right, just some pictures, sort of eye-candy pictures of the hardware. So this is one of the 8 satellites getting tested. And one thing I wanted to point out about this, just tying this back to CubeSats, almost all the hardware in this was bought from these third-party vendors that build subsystems for CubeSats. And really, this middle part of the satellite, right through the core here, in this little section right here, that's where all of the electronics are. The power and the avionics and the comm and everything is just in that little section in the middle, which is really a 6U CubeSat. And then everything else around it is just a bunch of structure that's mostly hollow, and it's just so that it's big enough to hold the antennas in place, because we needed antennas that were big enough to get the signal-noise ratio we needed to measure the scattered signal. And yeah, so that's what drove the side, but it's really a CubeSat with a bunch of extra wings on the sides to hold out the antennas. Here's 4 of the satellites going to thermal vac, the flight antenna or flight satellites, and here's one of the science antennas right here on the side. You can see how that antenna takes up almost the whole panel, and that's what made the satellites the size they were. It was because we needed a certain amount of gain. And then here's one of them getting its solar arrays tested, the deployment mechanism for it. And this is all 8 of them. This is just shortly before we mounted it on the top of the rocket. All 8 of them were launched on one rocket, 4 on the top tier here, and then 4 on the bottom tier here. And then they all went up into low Earth orbit, and then this deployment mechanism, which is this little tube in the middle, has these little springs that pop them out in different directions. And let's see if this works. Yeah, so this is a video. It's an animation that shows what the deployment looked like. This is about 14 minutes after launch. You're up in orbit, 520 kilometers orbit, and then these little spring-loaded things pop them out into slightly different orbits. Each one of these satellites have no propulsion at all. Okay, so the way we adjusted the spacing between them was by having slightly different orbital velocities, which made them settle out at slightly different altitudes, so they're moving at slightly different speeds from each other. We waited. It took about a month or a month and a half for them to spread out all the way around the Earth, kind of more or less evenly spread out. And then the ones that were higher up, we changed their attitude. We had reaction wheels to change their attitude. We changed the attitude, increased the drag, bring them down, change the attitude back so that we flattened them all out at the same altitude once they were all spaced out, and they hold the distances between each other once you get them all at the same altitude. And so that's the deployment mechanism thing. And actually, I just wanted to put in a quick plug here for this. There's a remote sensing conference that's going to be here in Pasadena in July, IGARS. Maybe some of you are familiar with that. And the plenary speaker, or one of the plenary speakers for it, is the guy who made this video. And he was a grad student in our department back in the 90s studying plasma physics. And he got really into computer animation to visualize the northern lights, the aurora borealis. And he got way more into the computer visualization stuff than into the plasma physics. So he dropped out of grad school. He didn't drop out. He got a master's degree and left, and came to Hollywood because he wanted to work in the movie industry doing, computer graphic stuff. And so he did that and became quite successful. And he actually got an Academy Award. He's gotten 2 Academy Awards. One of them was he did the tiger in Life of Pi. You've seen that movie? Yeah. This guy's really good. And so we sent him the CAD files for our satellite in the afternoon. And then that night, before he went to bed, he sent us this video. He did this for free in 4 hours. It's a really nice video. And so he's almost as good as Graham. He's almost as good. Yeah, so he's going to give a talk about how he did the Life of Pi in the plenary session at IGAR. So just a plug for this guy. Yeah. Joe Mankiewicz. He's really good. Okay, so here's the satellites all spread out after they're in orbit. And this is an example of the sampling that we get. This is after one orbit, 95 minutes, this is all 8 satellites making measurements of all these specular points. And then this is how it fills in over one day. So we get pretty good coverage. Most places, depends on the latitude. Near the equator, we see everything about twice a day. And then up near the top, around 35 degrees north latitude, we see things about 3 times a day. So it varies a little bit with latitude, and I'll show you an example of that in a few slides. But it's pretty good coverage, and it's because we have a whole lot of satellites. So here's a typical day in the life of our standard. This is our standard wind product this is from January 2022. But you can see there's a few storms here and there where the winds are kind of reddish and yellowish, and then yeah? 520 kilometers.
And they're just slowly dropping.
Yeah. So they were dropping about 1 kilometer a year for the first 4 years. Well, we've been up there a little over 6 years for the first 4 years. And in the last 2 years, it's gone way up. It's like 6 kilometers a year now. And it's because we're heading into solar max, and there's a lot more air density up there. So for the next 2 years or so, we're going to be dropping around 5 or 6 kilometers a year, and then it should drop back down again. Yep. Okay, so wait a minute. Let me go back here. Whoops. Going the wrong way. Oh, I know what I'm doing. Yeah. So this is This is that's the wind data, and then this is matchups between our wind retrievals and the Aero5 10-meter reference neutral stability winds. This is our standard comparison point. So that's the wind error as a function of wind speed, and down below 20 meters per second, it's fairly similar to NSCAD or QuickSCAD or all the standard ocean scatterometers for the retrieval uncertainty, but we have better revisit time just because there's a whole bunch of them. Okay, and now I'm just going to give you some pictures of some of our data products. So this is this level 3 gridded tropical cyclone data product that we assimilate into weather forecast models to see how much we can improve hurricane forecasting, and I'll show you some examples of that in a few slides. But anyway, these are just a handful of storms, Nicholas, Sam, and Grace, and then some zoomed in samples of where the storm is, and then kind of zoomed back global samples of the background winds everywhere. And then this is an example of how often we can make measurements. So this is one hurricane, Sam, and these are all the overpasses that we had over just a period of days during its rapid intensification phase. So you can see that most days we get 3 samples a day. This is a standard product that comes out every 6 hours. And there's a white spot down here because there just weren't any overpasses during that 6-hour window of time. But you can see the progression of the storm and the development, and there's gaps in these images because these are just specular points of that reflection. So it's not everywhere. It's only some places where we have a reflection, and so in between them we don't have wind samples. But you can see the structure of the storm. So that's an example of a wind product. And now we've taken these wind products. There's been a number of OSE studies, these observational system experiments. Is that what that stands for? OSE, where you take a bunch of satellite measurements, inject them into some forecast model with the new data, and then without it, which is the control, and then you see how much better the forecast gets when you add the data in. That's an OSE study, so we've done a whole bunch of those, and I'll just give you 2 examples. This first one is it's an OSE study taking Cygnus winds and adding them to HWRF, which is the operational hurricane forecast tool used by the Hurricane Center in Miami. And we're adding Cygnus data. We're considering a case where we use the standard operational input data and then a modified version of HWRF where we add the Cygnus data. Okay, so HWRF, you initialize it and then it runs. It's got this full dynamical model inside of it so that the hurricane will evolve numerically inside and grow and do whatever it's going to do, and that's how you do the forecasting, right? And so this is an example of one of many calculations that are done in the middle of HWRF as part of its forecasting to evolve the structure of the storm. And the one on the left, this is just one particular example of one of the many products that HWRF is calculating all the time. And this one is the wind field at 3 kilometers altitude. So it's one of a zillion things that it's calculating, and I'm using this one particular one just to make this one point. And so this is the wind at 3 kilometers forecast 24 hours into the future from when this forecast model was run. So it's a 24-hour forecast of the 3-kilometer wind. This is the wind field predicted without the Cygnus data. So this is the standard operational wind field, the control, and this is when you add Cygnus data to it. And the main difference between these two is the maximum wind, azimuthally, the maximum wind has shifted to the northeast, right, from more or less due north, right? And the thinking here is that, what we're really measuring, by measuring the winds at the surface, we're measuring the latent heat flux, basically, which is kind of forced by the surface winds, right? More wind, more evaporation of water vapor. And so we're getting this handle on the latent heat flux at the surface by having Cygnus winds that isn't available otherwise. And that's, the hypothesis is that's what's giving us more information about what the winds at 3 kilometers are going to be 24 hours later, okay? And the reason we picked this one particular, data field is because right at this one particular time here, so this is at this one particular time on this one particular day, 6 a.m. on the 25th, this forecast was run 24 hours before that. At this particular time, one of the Hurricane Hunter planes flew through this storm and made measurements of the winds at 3 kilometers. So we have in situ measurements to compare it to the forecast, right? That's why we picked this particular one. And this is what the airplane measured. And you can see that shift in the maximum wind field off to the northeast, right? So this is a little bit cherry-picked because we picked this one case that really shows this idea. But the idea is that there's extra information about the surface heat fluxes from the surface winds that should help the forecast. Okay, so this is kind of an internal process demonstration, that we have more information about the internal process, or more information that helps us predict the evolution of the interior process of the storm. And then at a kind of end-to-end level view of what this does, we also looked at the standard forecasts that are done of track and intensity for a storm to see how those help, and that's what this next study is. This is another OSE by a group down at the Hurricane Research Division. And so here in this OSCE study, again, we either use Cygnus winds or we don't use Cygnus winds in the standard HWRF model, or HWRF forecast tool. And in this case, we picked a different storm, Hurricane Michael. And the reason we picked Michael is because Michael had a blown forecast. There was this rapid intensification that was completely missed by the forecast and went from a Cat 2 to a Cat 4 over about 24 hours, and it was missed. You don't want to pick a case that had a really good forecast, operational forecast, because there's no room for improvement. So we picked one with a lousy forecast so that we can show off our improvement, right? That's the idea. So here's the track forecast with and without Cygnus. So the control is the operational, and then the with Cygnus is the green one. And there's a little bit of improvement. This is the error. This is the error in the track forecast as a function of time into the future. I forget what the benchmark is here, but the initialization time was like a day and a half before the rapid intensification event. Okay, so there's a little bit of improvement in the forecast of track. The Vmax, it's the maximum sustained winds, or the intensity of the storm. This black line here, that huge increase, this is the error. There's huge increase in the error is because the operational forecast missed the rapid intensification, basically. And when you add the Cygnus winds, we do a better job of picking it up because the errors are smaller. And then this last one, I think, is the minimum sea level pressure, which is also a good indication of the strength of or intensity of a storm. And again, with the Cygnus winds, it improves it. Okay, well, this is starting to click on its own here. Okay, so I'm going to shift gears now and look at our data products over land, because Cygnus runs all the time, 24/7. So over land, we have a number of things going on with the science team. This is an example of a really nice scope creep that NASA has been really supportive of, the NASA ROSES organization, because they've added new ROSES calls and new funding to our ROSES calls to get people to work on things other than hurricanes. There's about 1/3 of the people funded out of ROSES now are working on hurricanes with Cygnus, and 2/3 are doing other things. Some of them are doing other stuff over the ocean, and some of them are doing, about half of them are doing stuff over land. So one of the things over land is we can measure soil moisture. The surface dielectric properties of the surface are very sensitive to soil moisture, and that changes the reflectivity of the surface, which changes the scattering that we see. And I don't know why it keeps going this. So this is our data, our soil moisture, our standard soil moisture data product that we put out every day. It's actually every 6 hours. We have a 6-hour product and a daily product. And then this is just a matchup down here of one particular spot on the ground matching up against in situ measurements of soil moisture by one of the SMAP networks. So we're using the SMAPs has this big network of soil moisture probes that we can match up to. We don't have, well, actually we have a couple now, but we didn't have any at the beginning because we weren't planning on measuring soil moisture. But you can see that it tracks, these spikes in the soil moisture going up are rain events, and then this sort of exponential decay is the dry down phase after a rain event, and we're able to pick those up pretty well. So that's soil moisture. And then another, yeah.
What's the intrinsic spatial resolution of this soil moisture? That's also much smaller, isn't it?
Yeah, it's about 3 kilometers. Yeah, it's much smaller than SMAP. Yeah, 3 kilometers. Another thing that's sort of low-hanging fruit is the freeze-thaw transition of water. When it changes from ice to liquid, there's a huge change in the dielectric properties, and that makes a huge change in the reflectivity that we can see. So that's illustrated here. So this one was a little tough because we're at a 35-degree inclination, our orbit. So there's really only one place in the world, there's a couple places in the world, this is the biggest one, where you get reliable freezing every winter at our latitude range, and that's the Tibetan Plateau. So we spent a lot of time looking at the Tibetan Plateau and a lot of time looking at the Andes is another area. But here's the Tibetan Plateau, and this figure on the left is the first day in the year when the surface is thawed. So in the spring, somewhere between January and June, the first day it's thawed. And this is the first day in the fall when it freezes, okay? So just freeze-thaw transition. And you can take those two things and calculate how much of the Tibetan Plateau is frozen, what percentage or what area is frozen as a function of time. And that's what this plot is here, just the aerial extent of frozen ground as a function of time. You can see this huge seasonal signal, and if you had 10 or 20 years of this, maybe you could see climatic trends in things. But again, this really only works well for us in the Tibetan Plateau and the Andes. And you see these signals. I'm going to show you at the very end a couple of slides of follow-on or upcoming missions that are happening in the future with this technique. And they're all but one of them are polar orbiting, so we're going to get a lot more high latitude data with other missions coming up. So that's another thing that we can measure over land. And then another thing we can measure over land has to do with the nature of the scattering. When the surface is rough, like those pictures that I showed you earlier of scattering off the ocean surface. When it's rough, you get incoherent scattering. If the surface is really smooth, and smoothness is relative to the wavelength, GPS wavelength is 19 centimeters. So if the RMS roughness of the surface is significantly less than 19 centimeters, the scattering transitions from incoherent to coherent scattering. And when that happens, there's fundamental changes in the behavior of the data, which I'm going to show you a picture of, and then I'll show you sort of why in the next slide. So I'm going to, again, go back to SMAP, and I'm going to show you an image of SMAP made, an image of the Amazon River, a part of the Amazon River measured by the SMAP passive microwave instrument. So this is it right here. SMAP's got about, I think, a 34-kilometer footprint size, I think. So here's approximately 30-kilometer resolution image of this one section of the Amazon. You can see the main artery and then these little tributaries off to the side. So early in its mission, SMAP also had a radar on board, which had, well, it still has a radar, it doesn't work anymore, but it had a working radar, and it has about 3-kilometer resolution. So here's the same section of the river measured by SMAP radar, almost the same wavelength too, 1.2 gigahertz, the top one's 1.4, Cygnus is 1.6 gigahertz, they're all about the same. And so here's, the SMAP radar measurement of the same section. You can see that there's a lot better resolution of these tiny little tributaries and so on, okay? And now I'm going to show you the Cygnus measurement of the exact same spot, and it's got way better spatial resolution, okay? Way better than 3 kilometers. So soil moisture measurements have about 3-kilometer resolution. There's something fundamentally different happening here when you're measuring smooth water that's significantly smoother than the RF wavelength of 19 centimeters, okay? And I'll show you why here in the next slide. Okay, so there's, again, two different scattering regimes, incoherent and coherent scattering for specular forward scattering. There's two different types. This doesn't hold for monostatic backscatter measured by a standard sort of radar. But for forward specular scattering, it does. So with incoherent scattering, if the surface is rough, You know, all these roughness features here are large relative to the 19 centimeter wavelength. What happens is two things. One is the spatial resolution is fundamentally set by the delay in Doppler windows that generate that image of scattering cross-section versus time delay and Doppler shift. And each one of the little bins, it's set by the bandwidth of the signal, basically, the delay in Doppler bandwidths. The resolution, native resolution is about 10 kilometers, okay? And so that's one thing, is that. And then another thing is the power that you receive is related to the range of the propagation by this relationship here, where the GPS transmitter is up at 22,000 kilometers altitude. It's in a MEO orbit. And as the signal propagates down to the Earth, the power density goes down as 1 over r squared, because it's spreading out, right? And then when it hits the surface, you get all these individual little facets of scattering. And if the scattering from all these facets are incoherently added because there's so much roughness that there's random phase references from one scattering point to the next, then you just add the power scattered by each one of these points. And in that case, each one of these points is going to radiate out all on its own, and the power density will fall off as 1 over r squared on the way from the surface back up to the receiver. And you get this range dependence right here for rough surfaces, okay? If the surface is smooth, it's fundamentally different, and you get this relationship where the surface is perfectly flat. And inland water bodies, lakes and rivers, like 99.9% of them satisfy this condition. And what happens is the signal goes down, it reflects like a mirror instead of this random reflection process, and then comes back up again. And the range, or the received power, is proportional to this function of the range. It's just the total propagation length, 1 over r squared. And you can just use image theory and think of there being a virtual transmitter down under here, and the distance between the two is just the sum of those ranges, right? So the dependence on range is fundamentally different. And if you plug in the actual numbers for how high the Cygnus satellite is and how high the GPS satellite is into this equation, the difference between these two range dependencies is about 30 dB. It's actually about 34 dB. So it's a couple thousand times stronger, the received signal, when it's coherent. That's A. And B, the spatial resolution does not depend anymore on the delay in Doppler filters. It depends on this thing called the first Fresnel zone of the scattering, which is something that you deal with all the time in communications. But it's something that's just a few hundred meters across. It's like 150 meters across at low incidence angles and about 1 kilometer across out near the Earth limb, and the average is around 500 meters. So that's the fundamental resolution, is 500 meters. But if you remember that picture of the Amazon in the previous slide, there's features there that are way smaller than 500 meters. And the reason for that is because the scattered signal here, because of this range dependence, it's 2,000 or 3,000 times stronger over water than it is over the land near the water. Even if you have a tiny little bit of water that's way smaller than 500 meters across, the scattering from that water is 2,000 to 4,000 times stronger than it is from the land. So that tiny little bit of water will overwhelm the scattering from the land, and you'll be able to pick out those little tiny features. And one example of this is this reference swimming pool that we found in the middle of Iowa. There's this one guy that's got a swimming pool in his backyard, and there's no water within like 50 kilometers of that swimming pool. So it's a really nice point source, and we can image that swimming pool just fine. And it's just this regular swimming pool in this guy's backyard. Okay, so it's way smaller than 500 meters.
So another way I think of this is that the radiation reflected in the coherent case is really fundamentally being reflected in parallel radiation, whereas in this case it's being diffused out.
Yeah. And
you're left to collect it, or whatever the optic, whatever the detector area is, and the distance to, or the detector area to the scattering source. So it's just the geometry associated with parallel light versus diffuse light that gives you this same effect.
Well, there's a bunch of things. That's true. There's other things that are different also. Like if the signal is modulated, which GPS transmissions have all kinds of information modulated onto them for navigation reasons. The navigation code, the modulation, is all there when you go over a lake or a river, and it's completely washed out, okay? And I'm going to show you a slide later on about what you can do with that navigation information when it's there, okay? All right, so here's an example of what you do with this nice resolution of inland water. This is a before and after picture of the reflectivity of the surface before and after this one hurricane, Isaias, made landfall in late July 2020, and you can't really see that much difference. This is the difference between the two. And again, you can't see that much difference, but I'm going to zoom in on this one spot that got like wiped out by this hurricane, and that's the Dominican Republic. These regions here that are bright yellow, where the difference between them is really strong. Here, this is, I think, Santo Domingo, and then I forget what this is, part of Haiti up here, I think. Anyway, those two regions got really badly flooded. There was a lot of property damage and a lot of loss of life from this one hurricane, and we can image these floods really, really well with this technique. And then here's another example, Hurricane Harvey. Hurricane Harvey made landfall near Houston in I think 2017. And when it made landfall, it sort of stalled out right over Houston for about 3 or 4 days and dumped 60 inches of rain on Houston in a few days, and there was all this flooding. And so yeah, here it is right here. Here's the images that we made of the reflectivity over the course of a few days after landfall. And you can see this red region getting bigger and bigger and bigger because we're able to image the flooding. Okay, so that's an application. And again, because we come back around really often, we can get these time-lapse images on relatively short time scales of the flooding. Here's one more example. This is a much smaller feature, much less than 500 meters across. So this river, the Pascagoula River in Mississippi, it's the largest river in the United States that has no flood control at all. Whoops. There's no dams or anything. It's because there's a bunch of protected wetlands down towards the mouth of it, down near the Gulf of Mexico. So it's a really nice test case for, it overflows its banks every spring when there's a lot of rain, so we can go in and make measurements with it. Okay, so this is one particular flooding event in 2019. This is a stream flow gauge, a USGS stream flow gauge in the river, and you can see the flow rate goes way up and then back down again. So there was a flooding event right in here, and these dots are times when Cygnus went over the river. Okay, and when Cygnus goes over the river, we look at the reflectivity as a function of time, and these are the 5 time series of the reflectivity as it goes over the river. And here's the river right here for each of these dots, okay? So from this, we can measure the width of the river by looking at how big that spike is, all right? And then we take the width of the river and compare it to the stream flow rate to see how they're correlated. And again, this is a river with no built-up banks or anything, so when it floods, it's just going to overflow its banks. And this is a plot of the width of the river on the y-axis, the associated GNSSR width, that's what we call it. It's the width measured by the radar as a function of the flow rate. So there's this really high correlation. So there's 2 nice things about this plot here. There's a really high correlation between flow rate and river width. That's one. And another is, if you look at the scatter about that line here, the scatter is, 25, 50 meters, something like that. So that's the precision with which we can measure changes in width, tens of meters. And it's because we've got this super strong signal coming from the water, and around it is a bunch of land that's, with a scattering that's 1,000th as strong. Okay? All right, and I have one last example here, and this is river slope. And speaking of river slope, is SWAT back online yet? Yeah. It is, okay, good. Okay, so, right when SMAP went offline, we scrambled. We had our soil moisture data product that we were generating, and it was just this sort of little sidebar thing we had done. So every 6 months, we would run another 6 months of data and generate 6 months of soil moisture data from Cygnus. But then right when SMAP went offline, it was like sometime last year, we scrambled to streamline our data processing so that now we put out it's like a day and a half latency, and we put out a new soil moisture product every day now. And we could, so we could do the same thing with the river slope, but if SWAT's working fine, we don't need to. Right. So anyway,
but on the other, SWAT's every 2 times a month or 2 times every 2 weeks.
Anyway, we're gonna amp this up. Okay, so right, so here's a specular point track going across this one river. And when the river is smooth, we get specular reflections, coherent reflections. And when it's coherent reflections, all the coding information from the GPS transmitter is all there, and we can recover it, okay? And in particular, you can measure the phase of the carrier of the signal. So the GPS signal we're looking at is at 1575 megahertz and 19 centimeter wavelength. And we can measure the exact carrier signal, and then we can measure the phase of the carrier. and we can do basically carrier phase altimetry, okay, where you look at the change in the phase of that carrier, and you can figure out from that what the range to the scattered surface is. And we can measure the phase. When the signal's nice and clean and coherent like this, and it's strong because you get strong scattering off the surface, we can measure the phase to 30 or 45 degrees out of a 360-degree circle. So that's like 1/12 of 19 centimeters. Yeah, wow is right. So here's an example of the change in height along this river derived by carrier phase altimetry from Cygnus. And you can see the little bit of noise in this, that little bit of noise in that black line. That's the noise because of our inability to measure exactly what the phase is, but 30, 45 degrees, somewhere in there. And from that, you can get the slope of the river. And river slope, I mean, I'm not a hydrologist, but I've heard river slope is an important thing to know. It's one of the primary data products for SWAT.
Well, I mean, they use river slope and width to try and derive the stream flow.
Right.
With an assumption about the rest of the river. Those are the two.
Okay. So we can measure those. No problem. No problem. So anyway, yeah. So this is a really nice. This is stuff done by Jade Morton at Sea Boulder, and it's really nice work. She's working with a bunch of SWAT CalVal people to use SWAT CalVal facilities to validate this product, just like we're using the SMAP CalVal facilities to validate our soil moisture product. Okay, so this is my last science slide. So I've just got a couple more slides here about what's happening in the future, or even the present. Okay, so first, there's a couple of government missions that are in development right now. I say follow-on in quotes because they're not formal Cygnus follow-ons by NASA, okay? But they're follow-on-like. The first one is this mission called Triton by the Taiwanese Space Agency. They're getting ready to launch next month, and here they are with the satellite getting all buttoned up. This was an extra cosmic bus, which is the GNSS RO mission. They had an extra bus, and they did an in-house development of a GPS surface scattering receiver and put it on it. And this is in a low inclination. I think it's like a 28-degree inclination orbit because it's focused on typhoons. But that's going up really soon, so that's one. And then another one is HydroGNSS, which is an ESA mission, and that is going to be in a polar orbit, so they're going to be able to get all the high latitude stuff. Their primary objectives are soil moisture, freeze-thaw state, flood inundation, all these other land things that Cygnus was sort of uncovering over the last 5 years. Those are their primary mission. And then they also have winds as a secondary mission. And there's actually, this says single spacecraft right here, but this is actually wrong. They just announced a few weeks ago that they were going to fund 2 of them instead of 1. So there's 2 going up, and that's sometime next year. I'm not sure the launch date, but.
So what's the latitude coverage of that?
It's polar. Yep. So that's going up. And then there's 2 other things going on. These are private sector missions that are, one of them already exists. So Spire has flown a number of 3U cubesats with GNSSR receivers on them. And the first pair were these tech demo missions that had a very low duty cycle, less than 0.1%, but it demonstrated that the hardware worked. And then the second pair had onboard processing and not 100% duty cycle, but way more. It was, I forget, tens of percent duty cycle, I think. And it's generating data products, soil moisture and wind data products. And they have some other ones that are in development. So there's a whole product line going on at Spire to do this kind of stuff privately. And then there's another company which just got formed in 2021 called Muon Space up in Mountain View. And I'm working with this company. So we had and if you know what an ESTO IIP is, these technology development things that NASA funds, we had an ESTO IIP at Michigan that finished up about 1.5 years ago to develop a next generation version of this GPS scatterometer payload. And Muon has licensed the technology from the University of Michigan, and they're putting it into their satellites. And this is one of their, it's an EM, I think a qual unit getting tested up there. And they're planning on flying a constellation of a whole bunch of these. The first launch is later this year, and it'll have one of our instruments in it. And then they license all the technology so that they can build a whole bunch of them themselves for the later satellites. So that's another thing that's happening. And I think, yeah, that's it. Okay, so just in summary, there's a whole bunch of changes going on right now with small sats, private small sats, university small sats, government small sats. And there's some cubesats like Spire, and then some are bigger, like Cygnus is bigger, and the Muon one is bigger, but they're all small sat class. And there's a lot of things that you can do with them, either at all, because they have really fast revisit time, or just cheaper. Right, so yeah, they're cheaper. You can fly a whole lot of them in a constellation to get the repeat time down. You can try newer technologies because they're cheaper and because they go up every few years. And an example of that is this passive radar, GPS radar. That, you know, it was a relatively untested technique, but you know, NASA took a gamble on it because it wasn't a billion-dollar mission. And then Cygnus is doing its thing. We're doing the hurricane work that we originally proposed to do in our proposal, plus we've got all these other things going on over land with soil moisture, freeze-thaw, river width and slope. And then there's all these sort of follow-on missions that are happening with governments and in private industry right now. And yeah, that's it. Thank you.
If you're in the room and you want to take questions or you want to ask a question, please come up to the mic.
Thanks, that was a great talk. 2 questions. First, kind of a technical thing. You said the spatial resolution is limited by the first Fresnel zone, like 500 meters or something like that, but you get higher resolution. Is your data oversampled in space, and do you do deconvolution to get the higher resolution? How do you turn that 500 intrinsic into?
As with all tricky questions, the answer is it depends. If there's only one water body within a Fresnel zone, then you can see it without oversampling by taking lots of samples and compositing them together. But if there's a lot of water bodies nearby, you really need to oversample to be able to see them. So our standard product doesn't oversample enough. It samples at 2 hertz, so about 2.5 kilometers of forward motion of smearing, right? So we can't resolve complicated scenes with a bunch of different water bodies that are closer together than that with that product. We have a couple of different special operations products that we send up commands to the satellite ahead of time and say, turn on this or that special operating mode when you go over a particular scene, and we work out what time to turn it on. And then we can get the resolution down to 2 milliseconds. And we do that routinely. Typically, about once a day or so, we'll zoom in on some flood zone or something when there's a flood somewhere and turn on the high resolution mode just when the satellites are going over for like 30 seconds when it goes over some flood zone or something, and then we can back out all those fine features. So it's a little bit cumbersome. There's a bunch of like tech development stuff being done on these new missions to try to automate that kind of stuff. But right now it's all manual. Yeah.
Thanks. Second question on the assimilation into hurricane forecast models. Is any of that operational, or is it?
No, you know, I had this interesting conversation about a year and a half into the mission. Once we started demonstrating the value and showing there was positive impact on the forecast skill, I had this meeting with some NOAA NSDIS people. They came and talked to me about it, and the first thing they said was, well, first they said, congratulations, it looks like your data improves the forecast. The second thing they said was, there's absolutely no way we're ever going to trust a university-run mission for our operational data needs. Okay, that's never going to happen. And then the next thing they said after that was, so therefore, would you or your university be willing to license the technology to some company we can work with and that we trust for the long haul? Okay, and yeah, so I'm working with this company. Yeah.
Can I just throw in a little anecdotal example from cloud? So we had similar conversations in the very early days with NOAA, NSDIS, and folks.
Your JPL's got to be more reliable than the University of Michigan, aren't they?
I don't know, but maybe not. but you know what they said to us? We'll wait until ECMWF process the data and assimilate it before we begin to consider it. So it's just the lack of creativity or want to be creative.
Where's the camera here?
Just
it's up there. It's the lack of this. if you know what I mean. So this is exactly what happened with Spire. Spire was having a really hard time. Spire, the Spire surface reflection data is a little sidebar thing that they have like 6 satellites doing it, and they've got, I don't know, 80 or something satellites doing radio occultations, and many, many more. And that's their bread and butter GNSS remote sensing data product. And they are having a really hard time selling it to NOAA. And then they landed a big contract with EUMETSAT to use it operationally, and everything, the floodgates opened at NOAA. It's exactly the same thing. So, there's just something wrong with those. This is all being recorded, too. I really shouldn't say that much more. Yeah, so do the math. Do the math right there. Yeah.
That's a simple question. So you send in 8 units, now it's 7. So what happened to the one that's not operational?
Yeah, so we lost communication with it. This was late last November, November 26th. We talked to these satellites once a day in general, each one of them once a day, and on November 26th, we had our standard one-day, daily contact, and we brought down the data and all the standard engineering state of health, and everything was normal. And then on the 27th, when it was time to talk to it again, it wasn't there. It didn't answer. Okay, and we've never heard from it since. And we've tried many, many things, but yeah, it stopped talking on the 27th, somewhere between the 26th and the 27th. And yeah, it's really very frustrating. We've spent a lot of time on that 8th one, and we can tell what attitude it's in, even though we can't talk to it, because it's still tracked. There are these people that track everything up there, so we get these reports of exactly where it is. And so by looking at its trajectory, because we have no propulsion, we've got these models, these well-developed models of what the attitude of the spacecraft is as a function of its trajectory because of the orbital drag. So we can tell from that it stayed nadir pointed after we couldn't talk to it anymore, because the nadir pointed attitude is the minimum drag attitude, because the solar panels are kind of flat out like that. And it stayed in that mode for 7 days, nadir pointed, which means that the onboard data system was the onboard flight computer was still working, the reaction wheels were still working, it's power positive, all these things have to work or it can't stay nadir pointed. And then on the 7th day, right on schedule, it switched to sun point mode, because we have an onboard timer that says if nobody talks to you for 7 days, reboot everything and point to the sun and wait until somebody talks to you. And it did that right on cue on the 7th day. It switched to nadir pointed, which has a higher drag profile. And we saw that happen, and it's been in that mode ever since, and it's still sun pointed. And in order to maintain sun point, it means everything's got to be running on board to keep it doing that. So everything's working but the radio, for some reason. And it's now, the other ones are all dropping about 5 to 6 kilometers a year right now from drag. But in sun point mode, it's dropping about 20 kilometers a year because there's more drag, which is actually a good thing for orbital debris, that it's coming down quickly. But anyway, it looks like everything on it is working but the radio. So what are you going to do? Yeah.
There's just a comment online from Daniel Liminati that SWAT came back online March 9th.
Okay, congratulations.
And it's one measurement every 21 days to answer your query.
Yes.
Earlier in your talk, you mentioned that at any given point, there is a pair of GNSS satellite and your CubeSat that looks at a spot on the ground. So as the 2 units are flying, are you matching one to the other, or are you stitching data from different satellites?
Both. We have multiple channels in the processor on board, and it keeps track of all possible pairs that are visible. There's typically between 6 and 10 GPS satellites above the horizon visible from each of the satellites. So it calculates where each of the reflections should be. And it needs to know what the Doppler shift of the spot on the ground is and what the time delay is, so it can find it in delay Doppler space and then do its processing. So it's calculating all those things all the time, and then it does them in parallel. So we're making a whole bunch of different measurements at the same time from each satellite.
And then you're post-processing to create the image.
Yeah, yeah.
So the other question I had was, you showed a map of soil moisture of Houston, I think. What was the pixel size?
That one was 5 kilometers. Yeah, so there's a trade there. The finer the spatial resolution, the longer the time is needed to assemble the picture. So actually, I did a little bit of sort of sleight of hand to sell this. That beautiful picture of the Amazon that I showed you, that took a month to generate. And if I generate an image like that in a day or a week, the resolution won't be as nice, the spatial resolution. Yeah.
Okay. Thank you.
Yeah.
Great talk, by the way.
Yeah. Thanks.
So,
Becca?
yeah, great talk, Chris. I guess these small sats have a lot of capability these days, and you can still get them pretty cheap. So I can imagine the GPS receivers taking that much of the resources. So if you had a chance to fly with something else, would there be benefit in flying with some other instruments, or is it just kind of a standalone technology and missing?
No, lots of benefit. I mean, it's, well, the muon bus that you saw there, that's 75 by 75 by 100 centimeters. It generates a lot more power and has a lot more accommodation capability than that one little GPS receiver. So there's a number of other things flying on it. And I can't say exactly what they are. There's a bunch of other stuff flying on it. And for a number of different applications, but one of them is just, it's sort of a little baby version of that Aqua satellite where you get a lot more valuable science if you make measurements in multiple ways of the same spot, right? So, you could envision having something like Aqua, but maybe the size of, 500 kilograms instead of 4,000 kilograms, where you have a whole bunch of little CubeSat class sensors on it, and you could support that with a little satellite this big, right? Yeah.
One more question. Can you get any information about wind direction from your measurements?
We've tried really hard, and the answer is not easily. There's information there, but it's not strong enough to be able to get a reliable wind direction retrieval. The problem is right at the specular point, there's no sensitivity to wind direction, okay, for sort of fundamental electromagnetic scattering reasons. And as you move out the specular point, the dependence on wind direction grows, but the strength of the scattered signal drops as you move off, and those two competing things make it really hard to get it makes it impossible to get a reliable wind direction retrieval with our system. And we know what the dependence is on wind direction as a function of how far from the specular point is, and we know what the dependence of the signal strength is as you move away. So you can calculate basically how big your antenna would need to be, your receive antenna, to get enough gain, to get enough SNR. You can calculate how big it would need to be to get reliable wind direction information. And it's much bigger than our antenna. But in principle, you could design an instrument for the future that could do it. Yeah.
Yeah, great talk, thank you. I just had a quick question about that carrier phase measurement that you make with up to 45 degrees resolution, as you said. How do you reference that? What do you reference in that phase to, and what that resolution is limited by?
Right, so 45 degrees is typical. It's sometimes 25 degrees. I mean, it depends on the SNR. When you get a really clean signal, you need smooth water and a lot of water, like nice and wide, like a whole Fresnel zone across. Then you get a really strong signal. So 45 is typical. Actually, before I say anything else, I should say I didn't do it. Jade Morton and her group did it at CU Boulder. It's their work. And then, sorry, what was the last part of your question?
Yeah,
Oh,
what
the
is,
reference, right,
what's
right,
your
right.
phase
Sorry.
reference? Yeah.
Right, so these are, if you look at the y-axis on that plot of height versus time, it said delta H, or relative height. So you measure the phase relative to nothing, relative to what the phase was at time 0, and you look at how the phase changes over time, and that gives you the change in height. And trying to do absolute carrier phase altimetry is hard for a whole bunch of reasons. A lot of them are the same reasons it's hard to do absolute altimetry with a traditional, Sentinel-6 or Jason type instrument, right? Because of all the atmospheric corrections and all the ionospheric corrections and all those things. But if you want to get river slope, all you need is the difference between two things. And if these complicating factors like the TEC effect from the ionosphere or the wet delay from the troposphere, all those things are really highly correlated over a few kilometers, right? The humidity doesn't change much, the ionospheric density doesn't change that much over a few kilometers horizontally, then those things all cancel out. They're common mode errors when you take the difference to get the slope. So that's why it works well over short distances. Yeah.
Okay, no more questions. Let's thank Dr. Ruff one more time. Thanks so much. Very good talk.
Okay, that's a wrap.